This video will be the first video of several on the Enhanced Interior Gateway Routing Protocol, otherwise known as EIGRP. So let's just do a quick overview and introduction to get your feet wet. So EIGRP is now an open standard. For the longest time, EIGRP was actually a Cisco proprietary routing protocol. But somewhere around 2013, maybe 2014, Cisco actually put out an RFC for it, a document stating how it worked, and so now other vendors can also make use of EIGRP. So technically it's called an open standard. However, keep in mind that because Cisco did invent the protocol, if you're using EIGRP on Cisco devices, you're probably going to have access to additional features, additional ways you can tweak it or change it that you would not be able to do on non-Cisco devices. So EIGRP sometimes goes by the term as a hybrid IGP. Remember, IGP is what? Interior Gateway Protocol. Sometimes it's called a hybrid IGP. Other times you'll see it called an advanced distance vector. Either one is accurate. In this particular case, I actually like the term hybrid better because it actually does have characteristics of both link state and distance vector. For example, distance vector protocols do not build neighborships. A router running a distance vector protocol does not exchange any packets with any other routers around it, verify that anything is matching or correct before it will send its updates. That's not the way it works. In distance vector routing protocols, that router will just blindly send out its routing updates every so often, over and over and over again. And it will blindly receive incoming router updates. Now, link state routing protocols, however, do have to discover directly connected neighbors, exchange some information, make sure some things match, and then once that neighbor relationship is built, then they can exchange information. So in that way, EIGRP is more like a link state protocol. On the flip side, EIGRP is more like a distance vector protocol in how much visibility to the actual network topology a router has. In a link state routing protocol, a router actually knows the entire topology, not only the routers that it's directly connected to on its own subnets, but the routers behind them, and behind them, it knows how everybody's connected, who's neighbors with who, so it has a full topology map that's able to build by itself. In distance vector, that's not the case. In distance vector, if you and I were routers, I could send you a routing update about 1,000 networks behind me. So you would know from a layer 3 perspective what subnets live back there, but your actual view of the topology would just be you and me. In distance vector, I am your vector, I am your direction to get to those networks back there. You have no idea how many routers are sitting back there, how many routers are behind me, how they're connected. It's just sort of like a gray, fuzzy cloud behind me. You don't really know what it looks like. All you know is that there's networks back there, and you can use me as your next hop. So in that regard, EIGRP is more like a distance vector routing protocol. So all routing protocols, especially interior gateway protocols, when they transmit a prefix within a routing update, they will include some descriptive characteristic or identifier about that prefix to say what it takes to get there, how far away it is. In the case of EIGRP, it probably has the most complex metric of all the interior gateway protocols. So things like OSPF and RIP are real simple because they only use one value and one value only. RIP uses hop count. That's it. How many routers you have to hop through to get to that destination. OSPF uses something called cost, which is purely based on the interface bandwidth. Sort of like spanning tree, how spanning tree comes up with a cost based on bandwidth, and the higher the bandwidth, the lower the spanning tree cost. Same sort of principle applies with OSPF as well. Now EIGRP, and this is one thing that the proponents of EIGRP will point to when they say that EIGRP is superior than OSPF, is that the EIGRP metric is actually composed of several different variables that all go into one complex formula, and that formula spits out a really large number. And the metric is called distance. So RIP has hop count, OSPF has cost, EIGRP has distance. And distance is a big number that's a result of a formula that factors in many different values. You can see here the default is using bandwidth and delay. And we'll talk a little bit more about that in a subsequent video where I get into how the metric is derived in more detail. EIGRP supports manual and automatic summarization. Just as a refresher, the idea behind summarization is that, let's say that behind me, I know about every single network beginning with the number 20, 20.90, 20.1.1, 20.30.50, everything with 20. Well, rather than sending you all those thousands of networks I know about, summarization says, why don't I just collapse them all down into one entry, 20.000, and just send that to you. Say, hey, any packet you get going to a destination starting with 20, send it to me. So even though I know about all these specific routes, what I've sent you is a summarized view of those routes. So EIGRP supports manual summarization where you can actually configure that yourself. And at the CCNA level, you don't have to know how to do that. Or it supports something called automatic summarization, which quite frankly, you're not going to want to use because it takes the control out of your hands, and you have to have a really well-designed network right from the beginning to make use of automatic summarization. So most people don't even use it. EIGRP also supports authentication. The idea here being that with EIGRP, rather than just blindly accepting an EIGRP packet from a neighbor, they have to have the same password. If the passwords don't match, the neighbor relationship is not built, packets from that router are not trusted. This is optional. Don't have to configure it. And at the CCNA level, you don't have to know how to configure authentication. You just need to know that's something that you could do if you wish. And EIGRP supports unequal cost load balancing. This is the one thing that makes EIGRP unique from all of the other routing protocols. So imagine this for a moment. Let's take RIP as an example. Let's say that I'm a router connected to you, and I sent you a RIP route saying to get to the 90 network, it's a hop count of 3. That's what I send you. To get to the 90 network through me, it's a hop count of 3. Now let's say there was another router that you're also connected to who advertises the 90 network to you with a hop count of 5. Well, the default behavior is you would just use my route. My route is the best route. My route is the only one that you put in the routing table. But here's a potential problem. What if I'm sending you 200 routes, that other router is sending you the exact same 200 routes, but you're always preferring me because all the routes I send you always have a lower hop count than that guy, even though he's sending you the same routes. That means in your routing table, everything you get is going to come to me. Well, that might be a problem for me because potentially I'm getting so many packets from you and other people going to these networks behind me that I don't have enough bandwidth to start putting the packets on the wire. I'm running out of bandwidth. They're coming in so fast, I can't dump them on the wire fast enough to get rid of them. That's what's called congestion, where the packets start piling up in the router because it just can't put on the wire fast enough. So in that type of circumstance, you as a network administrator might say, well, those same routes are also reachable via that other router. The hop count is bigger, but hey, at this point, what does it matter? Because everything going to Keith, a lot of that stuff is being dropped. So it might be a better idea to just do some load balancing where we split the packets up and some of the packets go to Keith and some of the packets go to that other router. But here's the problem. RIP by default is not going to do that. It's going to say Keith's routes are better. They all have a hop count of 3. That other path, hop count of 5. So to do load balancing with RIP, we'd have to make both of these paths look the same. Now you can't really lower the hop count for that guy, so you'd have to do something in RIP pointing to me to say whenever Keith sends a RIP update, artificially add 2 additional hops to the hop count. make the hop count bigger. And so you'd have to do something to where the routes I'm sending you have the exact same hop count as his routes. Now, if the hop count looks the same, your routing protocol will put both paths into the routing table and you'll be able to load balance. So most routing protocols are like that. They will only select the best path if there's more than one path to a destination. And if you want them to put those 2 or 3 additional paths in the table, you have to tweak the metric in some way to make them look the same. EIGRP, you could do that. There are mechanisms to do that. But EIGRP, as it says here, supports unequal cost load balancing, which means it doesn't do this by default, and we'll have a video coming up in a little while on how to do that. But basically it means that if I send you an EIGRP update for 100 networks, and I say the distance, because remember that's the name of the metric in EIGRP, distance. The distance for all of these is 1,000. Now somebody else sends you those exact same networks, also via EIGRP, and he says the distance is 2,000. Well, in the world of routing protocols, lower is always better. So normally, you would just take my routes and install them into your table. But with a single command, you can actually tell EIGRP, take both sets of routes and put them in the routing table. Don't modify them, don't change the distance, just use them. So if you actually looked in your routing table, you would see, for example, for the 9090 network, you'd see 2 entries in your routing table. One entry pointing to me with a distance of 1,000, and another entry for that same network pointing to him with a distance of 2,000. So even though it did not affect the distance, they're still clearly unequal. You can now do load balancing between these 2 paths. EIGRP is the only routing protocol that lets you do that without forcing you to make them look like they're identical.